All matter in the universe is bound together by the force of electricity.
For instance, they could take this, a dull copper coin.
And of all the forms of matter, none exhibits the effects of electricity more clearly than metals.
Into solid gold. Gold. The stuff that dreams are made of.
Throughout the ages, scientists have dug deeply into the nature of metals. And in their quest, they've found that all metals have similar properties. For one thing, every metal is malleable and ductile, having the capability to change shape without breaking. Another age-old property is luster, the degree to which a shiny metal reflects light. For a long time, that was it. But in the 1700s, scientists found another property common to all metals. Today, it's called conductivity, the ability to conduct electricity. On an insulator, an electric charge stays where it is. But on a metal, it spreads out instantly. That is, the metal conducts electricity. On a deeper level, this is what happens. Each atom of a metal can be thought of as a positive ion with one or two loosely bound outer electrons. When two metallic atoms are very close together, the outermost electrons can pass easily from one to the next. As more atoms are added, electrons can range farther afield. Those mobile electrons are known as conduction electrons, and they give metals their special properties. In this way, all metals are electric conductors because every metal is like a giant molecule in which a number of electrons are shared equally by all the atoms. Picture it as a structure of positively charged ions, glued together by a fluid of mobile electrons. If a positive charge is brought near a metal, it attracts the mobile, negatively charged electrons toward itself, causing them to pile up at the nearest surface. The result is to leave net positive ions unbalanced by electrons at the far surface. The closer an electric charge gets to a metal, the more charge of the opposite sign builds up on the near surface, and more charge of the same sign is left on the rest of the surface.
And now an amazing little box I don't think you'll believe.
These properties are used in an instrument of science that may seem like magic. It's called a gold leaf electroscope.
Watch closely.
When an electric charge is brought near the metal disc, the gold leaf moves away from the rod.
Down. Float.
A positive charge near the top attracts negative charges, leaving positive charge at the other end of the metal rod, and the gold leaf is left with the same kind of charge. And of course, with the same kind of charge, the rod repels the gold leaf. When the wand is removed, the leaf falls back down, unless charge is transferred to the disc by physical contact.
Down. Float. Stay.
Physical contact leaves the rod and gold leaf with a net excess charge, and the leaf stays up. But it falls again at a touch of the hand.
Down.
The hand, which is itself a conductor, connects the post to the electroscope case. But where on earth did that extra charge go? The electroscope case is in contact with the Earth, which is a very big conductor in its own right. When contact is made, the electroscope, like any other conductor, shares its charge, releasing most of it into the larger body. Although in reality only negative electrons flow from one place to another, the effect is exactly as if positive charge flowed in the opposite direction. This is called grounding an electric conductor, or simply grounding. And for all practical purposes, when it happens, the conductor becomes electrically neutral.